the Jovian planets. Okay, so even though we knew a little bit about Jupiter and Saturn without spacecraft, we didn't really know a lot about them. And so any detailed knowledge about any of the planets, including Jupiter and Saturn, actually came from spacecraft rather than ground-based telescopes. There's been a bunch of spacecraft that we've sent out there. Voyager 1 and 2 were sent out in the 70s, and Voyager 1 wanted to go around Jupiter and then around Saturn. Voyager 2, Saturn, and then off to Uranus and Neptune. And these guys studied the EM fields of both Voyager and Saturn, and Uranus and Neptune. They also looked at them through different fields of light, right? Radio, visible, and infrared. And they sent data back to us so that we could analyze it. So this is actually pictures of Jupiter. Galileo was launched in the late 80s and arrived at Jupiter in the mid-90s. It had an atmospheric sensor on it. And so what it was trying to do was get the chemistry and the layout of Jupiter's atmosphere. It was also going to go to Jupiter's moons and look and see what was going on over there. We won't get to the moons until chapter 8, which is the next chapter. Cassini went to Saturn, and that one was launched in the late 90s. It also went to Titan, which is one of Saturn's moons. Again, we'll talk about that in chapter 8. And it just stays in orbit with the moons. So it studies the planet, the rings, and the moons. And it's still going. Its mission's still pretty good. It hasn't broken down yet, so they just kept it there. So this is a chart comparing all of the Jovian planets, and they did put, actually it's all of the planets, never mind. And so you can see everything's compared to Earth, right? Earth is one mass, one radius, one surface gravity, one rotational period, or one solar day. Magnetic field, 1, right? So if you look at the mass, Jupiter, Saturn, Uranus, and Neptune are all many, 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 many times bigger than Earth. So a lot more mass. If you look at radius, again, the same thing. They're a lot bigger than Earth. Gravity, compared to Earth, everything except Neptune is bigger. And interesting about that. Surface temperature, everything's a lot colder. And magnetic fields, they should be stronger. That's odd. But what I do want you to look at is the average density. So Earth is 5,500 kilograms per meter cubed. Jupiter, Saturn, Uranus, and Neptune are all 1,000-ish. Right? Neptune's actually a little bit denser, and Saturn's a little bit less dense. So in general, they're huge, right? A large mass, a large size. However, they have a low density. Technically, Saturn's density is so low, it's lighter than water. So they like to say that Saturn could float. I'm a little bit wrong with the physics of that, but that's okay. Saturn has a density less than water, so Saturn technically, theoretically, could float. So what are these guys made up of? Hydrogen and helium. That's pretty much it, hydrogen and helium. Now on Earth, these gases actually have a really low density. If you look at the periodic table, hydrogen and helium are the lowest density, or the lightest gases on the periodic table. It's number 1 and number 2. So how come they have so much? Well, because they have a lot of gravity. And the gravity works to keep the atmosphere together. So rather than losing its original atmosphere, like they think happened to the terrestrial planets, it kept everything. And because it kept everything, it had more mass, so it has more gravity, and so it can attract and keep a lot more of its atmospheric gases, whatever. So it's thought that the Jovian planets have a core. And if they do have a core, they're thinking it's either a rocky or an ice core. They also have EM fields. And where they come from, we think it's because of the rotation of the mantle, and we'll get to that, but they do have an EM field. They also emit radio waves. So they may not emit visible light, but they do emit radio waves, which is interesting. Okay, how do they rotate? Well, like we had said before, Mercury is almost straight up and down, Venus is upside down, Earth and Mars are pretty much a 24-degree tilt, Jupiter is pretty much straight up and down, Saturn is just a little bit more tilted than us, 26, 27 degrees, depending on which variation you read. Uranus is on its side at 97 degrees, and Neptune is about 30 degrees. Alright, so one of the first things we want to do when we discover a new planet is find out what its rotation is. Well, usually we look at something on the planet, and like a crater or some sort of structure, and you can watch that go around. However, there's no solid surface for Jovian planets. So it was kind of hard to figure this out. And once we did, we figured out there's something called differential rotation, where basically parts of the planet are rotating at different speeds than other parts. This also happens with the sun. So Jupiter, at the high latitudes, it actually takes 6 minutes longer to go around the high latitude than it does to go around the equator. Saturn, there's a 25-minute difference. And Uranus and Neptune, the poles actually rotate faster than the equator. Uranus has a 2-hour difference, and Neptune has a 6-hour difference. So it's kind of interesting that if you're on the middle, you're going to go around the Earth, the planet, differently than at the pole. You're 6 minutes up to 6 hours. So what's on the inside of a Jovian planet if there's no solid surface? I can't really see past the cloud layers, and there's no seismic data to let us know there was I want to say earthquake, but a Jupiter quake? I don't know. But there's nothing there that we can actually get any information on. So we built physical and chemical data and what we think it could look like, and those are the models that we have. All right, so on the inside of the Jovian planets, we think they're all kind of similar. They've got a core, kind of not a bigger core for Uranus and Neptune, but percentage of the planet has got a bigger core. And then they have a mantle, and the mantle is actually pretty interesting. It's made up of hydrogen. However, not hydrogen like you would think, like a gas. The hydrogen's actually compressed so much that not only is it like a icy, or slushy texture, but it's also acting as a metal. So it's got this metal liquid as a mantle. And then on the outside, or the crust, I guess, that would be your atmosphere, like the entire atmosphere of the planet. So there is no crust. It basically goes atmosphere and then this slushy hydrogen and then a core. Granted, the core could be rock or ice. We're still not entirely sure. So the next slide is going to have a not so exciting video of taking apart the Jovian planets. It's worth a look. But the slide after that is actually going to have a crash course for Jupiter. So make sure you have that worksheet ready.
This animation begins by showing the comparative sizes and colors of the Jovian planets. We can artistically take them apart, revealing their relative innards. All of these gas giant planets, especially Jupiter and Saturn, emit more radiation than they absorb, suggesting great heat within them. Jupiter and Saturn have very similar interiors of mostly hydrogen. Somewhat by contrast, Uranus and Neptune are also thought to have nearly identical structures and compositions.